Hello everyone, welcome to the video on Information Technology and Cross Entropy by Society of Artificial Intelligence or SOAI. I am Ritul and these slides are created by my colleague Tushar. Let's start. Information theory and cross entropy expectation. Consider the example given below. Let us consider the random variable x that maps to the winning team amongst the four teams A, B, C and D. Probability of X represents the probability of team X winning where X belongs to A, B, C and D. Consider G of X, the gain associated with each of the team if they win where X belongs to A, B, C and D. Now, the expectation that is E of X is given by sigma of I where I belongs to A, B, C and D and the probability of x which is equal to I here multiply by gain of x which is I. Consider the following data. Here in this table there are three columns which are x, probability of x and gain of x. Here the column x denotes the teams which are A, B, C and D and corresponding to the probability of x and gain of x. Here, the probability of A is 0.4 and the gain is 10,000. Probability of B is 0.2 and the gain is 2000. Probability of C is 0.1 and here the gain is negative, that is the loss, which is 8000. And the probability of team D is 0.3 and gain is 5000. Therefore, expectation of X is equal to probability into the gain, which comes to the 5100. Consider the random variable SR, which maps to the direction in which the sun rises, east, west, north and south. Now, we are told that probability of SR, where SR is east, is 1. Here, this is almost a blatantly obvious truth. Thus, we can say that the information gained here is very low. Consider another random variable st, which maps to the whether there is going to be a storm today. Yes or no. Now, we are today that probability of st is equal to yes. Then the probability comes out is 1. Here the information gained is very high and this is a rather surprising that is low probability event. We can almost say that information content is directly proportional to surprise, or in other words, information content is directly proportional to 1. Thus, it can be inferred that information content is a function of the probability of the event. Here, IC is the information content and IC is probability of X, which is here X is equal to S. Now, consider two separate events. X maps to which cricket team won the match, where A, B or C or D. Y maps to the state of a light switch, that is on or off. Now, we are told that team B won the match and the light switch is on. The total information gained is IC, which is X here is equal to B and intersection with Y, which is on, is equal to IC of X is equal to B plus IC of Y, which is on. Combining the points from above, we have IC where probability of X is S, information contains a function of probability. And from the previous example, IC of probability X intersection Y is equal to IC of probability X plus IC of probability Y. From probability theory, if probability of X and probability of Y are disjoint, then probability of X intersection Y is equal to probability of X into probability of Y. Therefore, IC of probability of X into probability of Y is equal to IC of probability X plus IC of probability Y. Therefore, we need a family of functions that satisfy function a dot b is equal to function a plus function b. The log function satisfies this log a dot b is equal to log a plus log b. Here the dot represents the multiplication. Now we can write the IC function as follows. IC of x where x is a is equal to log function of 1 probability x is equal to a. You can see in the three statements. IC of x is equal to a is equal to log 1 minus log probability of x a. IC of x is equal to a is equal to minus log of probability of x with base 2 is equal to a. That here a represent all the logs used base 2. The above is the new formula derived which includes the surprise probability, that is, the surprise is an event means it has low probability, higher the surprise, lower the probability. Here we are going to study about entropy. First, a quick recap of the concepts we have studied so far. Here there are four columns. We have random variable x where the x is teams A, B, C or D, and the second column probability distribution where probability of x where x is equal to A, B, C or D. Information content, that is IC, and expectation, that is E of gain. So here the probability distribution of A has the information content, that is IC, which is equal to minus log of P where x is equal to A with base 2, and same are for team B, team C and team D. And you can see here the expectation, that is E of gain, is comes out summation of I where I belongs to A, B, C and D. Probability of x is equal to I multiplied with gain of x is equal to I. You can see in this formula. Based on these four concepts, we can talk about entropy. Entropy, h of x, is the expected information content of a random variable. H of x is equal to minus of summation of probability of x or p of x, that is I belongs to A, B, C or D, which is equal to I. Basically, substitute gain for information content in relation to number of bits. Consider the entropy equation from the previous section using shorthand Pi for probability of x is equal to I. Here Hx is equal to minus sigma I where I belongs to A, B, C and D, and the Pi into log Pi. Suppose there is a message X that you want to transfer that can take four values in A, B, C and D. For four values, we would use 2 bits to transfer each message. Here in this table, you can see this random variable X, 2 bits version, probability distribution and information content, that is IC. Here for team A, the 2-bit version is 00 and the probability distribution here is 1/4 and the IC is equal to minus log of 2 to the power 2 with base 2 is equal to 2, that is log A with power n with base A is equal to n. It's a formula actually. And similarly for random variable B, C and D. Now we can make the connection that the number of bits required to transfer a message is equal to the information content of that message. Consider another message X with 8 values A, B, C, D, E, F, G and H. Here the 2-bit version for A is 000 with probability distribution 1/8 and IC which is equal to 3. You can see in this table. And same for other random variables apart from the 2 bits version, that is for B 001, for C is 010 and so on. While sending a continuous stream of messages, we would be interested in minimizing the stream of bits that we send. Consider the same 4-valued example but with a different distribution. Here random variable X with probability distribution and information content. For random variable A, the probability distribution is 1/2, which is high probability, and IC is minus of log 2 with power n with base 2 is equal to 1 as the previous slides. And for random variable B, the probability distribution is 1/4, which is medium probability, and IC is minus log 2 with power 2 and base 2, which is equal to 2. Similarly, for random variable C, here the probability distribution is 1/8, which is low probability, and IC is 3. And for random variable D, here the probability distribution is again low, which is 1/8, and the IC here is 3. This situation is considered favorably only if the average number of bits is less than the value it takes for an equally distributed set of values. The average is calculated using entropy h of x, which is equal to sigma pi multiplied with log pi, and here I belongs to A, B, C or D. Again, average divided by entropy is equal to probability distribution and IC, that's information content, which is equal to 1.75 and smaller than 2. Thus, the entropy gives us the ideal number of bits that should be used to transmit the message. It shows that we required 1.75 bits to transfer a message. Consider the following data. Here in this table, there is a random variable x with a, b, c and d, true distribution y, true IC, that is information content of x, predicted distribution y and predicted IC of x. You can see in this table, initially we do not know the values of the true distribution and thereby the true information content. Hence, we generate a predicted distribution and used to compute the predicted information content. But the actual message will come from the true distribution y. So therefore, the number of bits will not be minus summation of y cap I log y cap I, but instead is negative of summation y log y cap I. This is because the value associated with each of these messages come from the predicted distribution, but the message themselves comes from the true distribution y. Now we have formed the basic to talk about KL divergence. Here hy is equal to minus of summation y log y is called the entropy II. Here h minus y log y cap is called the cross entropy. Y comma y cap is equal to summation I. Now we want to find the difference by distance between the predicted cases and the true cases using something more efficient than the squared error. Here in the statement D and E, you can see this, it's the KL divergence. Now we have a way of computing the difference between the two distributions. Consider the example. Here x and y which is we don't know initially, and y cap is predicted using sigmoid. For variable x which is t, here the y is equal to 1 and the y cap is 0.7. For nt, the y is 0 and y cap is 0.3. A signboard with the text Mumbai, a random variable x which maps the signboard to text comma no text. The distributions are as follows. Previously we were using squared error loss is equal to summation of y of I minus y cap I. Now we have a better metric, one that is grounded in probability theory, that is KL divergence. We aim to minimize loss by KL divergence with respect to the parameters W and B. From KL divergence equation, we can see that yi doesn't depend on W and B. So therefore, we are really only trying to minimize the first term, that is the cross entropy. So in practice, we can treat the second term as a constant, and the equation would really be minimum of minus sigma I by I log y cap I. Here I belongs to t comma and t. Cross entropy loss is equal to minus 1 multiplied with log of 0.7 minus 0 multiplied with log of 0.3. The second term cancels out and we are left with minus of log 0.7, which is the same as minus of log y cap for the true case. It can be called negative of log y cap c, where c can take the value 0 or 1 which correspond to NT. Using cross entropy with sigmoid neuron, consider an example in the scope of our final project. Look at the following signboard. Here the signboard represents Mumbai. X is equal to image, y is equal to 0 or 1, that is true distribution where I corresponds to the text. Y cap here is equal to 1 by 1 plus e of minus w dot x plus b. Here dot represents the multiplication. This corresponds to y cap is 0.7. Thus the predicted distribution is equal to 0.3, 0.7, where 0.7 corresponds to text. The loss function is L of theta, which is equal to negative of summation I yi log yi, where I belongs to 0, 1. This is the graph on the right side with x-axis from -8 to +8. It represents wx plus b, and y is from 0.0 to 1.0. And this you can see in this graph. Consider two examples side by side: training data, image, L of theta, and loss function. The loss function can be expressed as follows: L of theta, which is equal to minus log of y cap, is if y is equal to 1. Log of theta is equal to minus log 1 minus y cap is y equal to 0. Combining them and removing the if conditions, we get to know L of theta is equal to negative of combined 1 minus y log I minus y cap plus y log of y cap, where y is equal to 1, the first term becomes 0, and when y is equal to 0, the second term becomes 0. Now, learning algorithm for cross entropy loss functions. From the previous step, we have L of theta, which is equal to negative of 1 minus y log 1 minus y cap plus y log y cap. You can see in this very first line. Cross entropy laws only make sense for classification problems. The rest of the procedure is the same as the sigmoid neuron, except we use cross entropy to minimize the loss and choose the best parameters w and b. Initialize w and b randomly. Iterate over data, compute y cap, compute L of w comma b, where L is the cross entropy loss function, and wt plus 1 is equal to wt minus eta with delta wt. Similarly, bt plus 1 is equal to bt plus eta with delta bt. PyTorch or TensorFlow have functions to compute and till satisfied. Number of epochs is reached, that is 1000 passes per epoch. Continue till loss, where it is smaller than exception some defined values. Continue till loss w comma b with t plus 1, which can be equal to loss of w comma b in t. Computing partial derivatives with cross entropy loss. Loss function of L theta, which is equal to the same as we studied in the previous slides, and consider delta w for one training examples. You can see this is the derivative formula here, and the final derivative is the first part multiplied with the second part. You can see all these statements are belongs to the previous slides, where in this video we had talked about. And finally, when then plug the values of delta w and delta b into the learning algorithm to optimize the parameters w and b. Code for cross entropy loss function. These are the changes that are made in the squared error loss function code. Code for cross entropy loss function. These are the codes that are made in the squared error loss function code in the previous videos, and the changes is what we has to do the changes here in the error function, in the grad underscore b function and grad underscore w function. Here you can see this statement is changed. We has to replace this statement from this statement, and all the function is same as the previous one. And here this function, here we return these functions, and here we have to return only this, that is fx minus y. And similarly in the grad underscore w function with parameters w, b and x and y, we have to return only fx minus y multiplied with x. You can see the difference in here, and the final result that will come out is delta w is equal to y cap minus y and multiplied with x. Thank you.